pleasure to introduce friend Video and Montana this morning. I'll give the talk on the Ricci Solitons, and then we'll have two in the afternoon with the Ricci Flow by Curvature and the Ricci Flow and Michael. So we'll be having exciting activities today. All right, so let's start with the first one, geometry of Ricci Solitons.
Thank you for the invitation. It's a pleasure to be here. I came about 2 years ago, I think. It was a different building, and I enjoyed it very much. It's good to be back. So let me just outline. So this is an outline for all 4 lectures. And so there are 4 lectures, but I have 3 sections. So somewhere I'll have to split. So one is just basic facts. This will be very short because it's my understanding that you've seen this already last week. So I'm just going to recall and set up the notation, but I'm not going to explain much of this. And then I'll talk about, well, I'll say classification. It depends in what meaning you mean classification. So I'll just say it and I'll explain at the right time. Classification of shrinkers in 4D. So these are types of solitons. I'll explain in a moment the terminology. And the last part will be the same thing. And this will be steady. It will be 3D. So it's not done yet. I'm not going to announce that we finished the classification. That's why I put it in comments. So it's just going to be some details and some open questions. What's left of the classification. So let's just start with the first one. So basic facts. So a Ricci soliton means the following. So you have a Mg, and this will be complete, compact or non-compact, but most times will be non-compact. And suppose there exists a smooth function so that the Ricci curvature plus the Hessian of that function is a multiple of G. So that multiple is typically -1, 0, or 1. And so it's a scalar number. And that's what Ricci soliton means. So I want to explain very briefly why these are important. They are important because we studied them in the Ricci Flow, which is the topic of some of the lectures. So Ricci Flow, which is dg over dt, is -2 Ricci. And how do I construct such a flow? So this is a time dependent. There's no time there. How do I construct a Ricci flow from a Ricci soliton? You can take the gradient flow of f, more or less. So, of course, depends on lambda. So you can see this becomes a problem if, say, lambda is 1 and t is 1. This is a problem, right? So this will be defined, for example, when lambda is positive, will be defined up to 1 over lambda. So that would be called an ancient solution. If lambda is 0, of course, this will be defined for any t. So you take this and then define g of t. this way, then this is a solution of the Ricci flow. So that's the relation. These are called self-similar solutions. So self-similar solution means that the flow is given by some function. So the flow is something like some function multiple of a pullback of G by diffeomorphism. This function in my case is 1 minus lambda t. And when lambda is positive, the speed is negative, so it shrinks. That's the terminology. So when lambda is positive, so sigma of t is just 1 minus t. The derivative is negative 1. It shrinks in t. That's called shrinker. So that's the name for the second part. I'm interested also in lambda 0. That's called steady Soliton. This exists for t from negative infinity to 1. This exists for t between negative infinity and infinity. And finally, when lambda is negative 1, you get expanding. So I'm leaving expanding out of the topics because there's not enough time to cover it, but also because these two are much more important. So the reason we studied them is in the Ricci flow, in the singularity analysis of the Ricci flow. The possible singularities are modeled either by this one or this one. So if it's type 1, it's
you mean if we start with compact?
If you start with the compact and it has a finite time singularity, then when you blow up the singularity, it's not really proved yet, but it's expected that, say, in dimension 3, all you get is a sphere, a cylinder, those are the shrinkers, or the Bryan-Soliton, that's the steady. So it's so they model the possible singularities of closed Ricci flow. So I'm not going to go into that, but that's the reason why we study them. So it's not just a very special solution, it's the type of solutions that we need when we study singularities. So I guess I'll give some examples, but very briefly because it takes a lot of time to compute everything. So I'll just more geometric. I'm just going to say how the geometry looks like. I'm not going to do the details. So and again, I'm focusing only on these two. And I'm leaving this one out. So for examples, so for shrinkers, in the shrinking case, we have the so-called Gaussian. This is not that important for Ricci flow, but it is a good example. I mean, it is an important example to motivate some questions. So this is R on Rn. You take the usual metric, and then you need to take the function to be the distance function squared. So that's the example. So this itself is not important because it's flat, but its product so this, the so-called cylinders, these are important. So here I'm viewing this one as the Gaussian, and this I'm viewing as Einstein. So F is constant. Then it is a product, and it is a solution of the equation. So these are the trivial ones. It turns out in dimension 3, that's all. Dimension 2 and 3, that's all. In dimension 4 and higher, there are other examples. So let's just focus on dimension 4. because, as I said, I'm interested in the second part in the classification of 4D stringers. So there are many other examples in higher dimension, but this is the one I'm interested in now. So the starting point is you try to transform the PD into ODE, because that's pretty much the only way you can solve it. So on C2 you try a U2 invariant metric. So that means you try the metric G. You try a complex metric. So this will be a function, so dd bar of a potential P, where P depends on R. R is not Z squared. R here is a log of Z squared. So that's the notation. And in Scalar geometry, of course, you have very useful formulas. What you need is determinant of G is e to negative 2r p prime p twice. That's a computation. So it's something you can get from here. And then Ricci plus the Hessian. Because of Scalar geometry, this becomes G, not 1/2 G. So this actually is a system where it means in complex coordinates one equation and another equation. So there's no G, there's no Ricci. It's a Scalar manifold. So you get this system of equations. It actually, the Scalar geometry helps you to solve it. And first of all, this means Ricci. So there's a useful formula for the Ricci curvature. Plug it in the first equation. You get minus log determinant of G plus P, plus F is P. So that's what you get. Then of course it's only natural to say, let's make these two equal, right? So what I'm trying to say, of course, I cannot finish this computation because it's not that easy. In the end, it's an ODE. But I'm trying to show you how it starts, and that's most times it's very important. So the first equation becomes something trivial. I'm just going to take F to be this. So I have no worries about F. In general, in a Riemannian manifold, if I have that equation, I'm very worried where does F come from. So here F is just easily computed, and it's P plus log of determinant of G. So exactly that thing over there. So that's why we need this formula. So it's a second order quantity in P. Then you plug it in here, right? So of course it's easy to see that take two more derivatives becomes fourth order in the function in P. So it's a fourth order equation in P. But you can do better than that. So there are some simplification, and eventually it becomes a second order equation. So there's a trick and becomes a second order not necessarily in P, but actually in P prime. So it's not an equation in P itself. That part is not too hard to see that actually here you have P prime and its derivative. Take more derivatives, of course it's just an equation in P prime. So it's a third order in P prime. You can reduce it to second order, then you can solve it, but you don't get an explicit solution. You get some solution which you can understand geometrically. So that's the part I'm interested today. I'm not going to finish that computation, but I'm going to tell you how it looks like geometrically.
So maybe just to add a comment. The second equation, essentially gradient is holomorphic.
So that's the trick that allows you to simplify that. So from second order, from that second order equation in F, you can simplify indeed by seeing that gradient of F is a holomorphic vector field. And computing that allows you to simplify. So how does this look? I mean, you can get the solution, and it's not explicit. So all we know is how it looks like at infinity. And it's cone-like at infinity. Actually, the solution, so G was dd bar of P. P itself, P of, maybe I shouldn't say R was log. So P is just like Z to root 2. So it's not R, this is, R was log of Z. So this is just like, P behaves like this at infinity. So at infinity, when you solve this equation and the second order equation and you compute the asymptotics, this is how P looks like at infinity. And that's very important. So you know how the manifold looks like. So the metric G will be dd bar of Z to the root 2. But this is at infinity. It's not everywhere. That's a cone metric. It's actually a Scalar metric, and it's also a cone. So you have a metric. This is the cone, and then you have a Soliton, which it's not a cone itself, but it's asymptotic to a cone. So this is the shrinker. The problem with this is that, I mean, I said a lot of things. You have an OD, second order OD, but when you have ODs, you have conditions, right? Initial conditions. It looks like you can have families of solutions, and I didn't say anything about that. I said there's only one, not a family. So that's because this is a ODE, but it has geometric initial conditions. The metric has to be well defined in the origin. The metric has to be complete. So it's not an ODE second order with P prime of 0 is this and P twice is something else. It has different kind of conditions. That forces you on one hand to have only one P, so there is no family of solutions, it's only one. This is called the Fick Soliton. So Feldman, Hillman, and Knopf. And it's the only one we know in 4D that's not a cylinder, so, and which is non-compact. So the only non-compact one that's not a cylinder. And it's unique, but also when you try to say in 0 how it looks like, so 0 meaning R being minus infinity. So when you try to see that, you never get a complete metric in 0. So actually this Soliton is not defined on C2 itself, but it's defined on blow up of C2 in 0. So it's you replace the origin with a sphere. And that's the space where this is defined. I'm not too interested in that right now because all I care for the moment is how it looks like at infinity. So here it's not, it has some topology. At infinity it's asymptotic to a cone. And that's the Scalar metric of the cone. As a cone, it has curvature, so the curvature decays like distance squared, and the volume grows like it's maximal. So it has maximal volume growth, and curvature is decaying quadratically. Very important here is to note This is again something that you compute from the ODE and check that the curvature is not positive for this example. So in 3D, there's an important estimate that says all the shrinkers or all the ancient solutions in general have positive sectional curvature or non-negative sectional curvature. This one does not. In fact, Ricci in the gradient f direction is negative. So I should say so it's decaying faster. It's very fast. It's not quadratic. It's faster than quadratic, but it is negative. So that's a very important observation for this example. Okay, so that's an example about for shrinking Soliton, and I cannot do all the details, but this is the geometric information we have. Similarly, you can do in for steady solitons. I will need this for the last section. So for steady Ricci solitons, you have similar properties. Similar constructions, and so on one hand. The one that is going to play an important role is the so-called Scalar. This is something defined on R2. And it's just a computation. Anybody can check this. So if there's no one here, that's a cylinder. So and if you add that one, it has only one end. And it looks like a cylinder towards infinity. It has positive sectional curvature. But you close the end of the cylinder. So basically, that's the name, Scalar. The function f, which makes it work, is log of the same quantity. And this is the only one in 2D that's complete. And so this is the only example that's complete. So that's one example. And again, there are many other in higher dimension, but I'm interested in only in dimension 2 and 3 this time. In R3, there's the so-called, in 3 dimension, there's the so-called Bryan-Soliton, which it's not as explicit as this one, but it's still something that you can compute. You know almost everything about it. I should add here that because it's a cylinder at infinity, the volume, it grows linearly. The curvature actually, the Gaussian curvature decays it decays exponentially in distance. So K means the Gauss curvature. So for the Scalar, the Gauss curvature decays very fast. It's exponential decaying. And again, volume is linear because it's cylindrical at infinity. There's another example in dimension 3, which is very important. It's so-called Bryan-Soliton. So this one is kind of that type, where you try to solve it by ODE. It's the only rotational symmetric example that you can construct. But it's not as explicit as this one, so I cannot write it up. I cannot write up the metric. However, you know the geometry. So the way you construct is you look on R3, and you look for a metric which is dr squared plus some function d theta squared, right? So you look for a rotationally symmetric metric, and you have another function, the potential, which is also rotationally symmetric, and try to find out if there's any omega and f that will work. And there are. So you can make it work. This time it's not a fourth order. Curvature is 2 derivatives in omega, so it's a second order system. Trying to show that there is a solution. We're not that interested in precisely how to solve the ODE today. We are interested in the geometric property. So how does this look like? It's a paraboloid at infinity. So that means the volume doesn't grow linearly anymore, it grows quadratic. So it's, that one was maximal, this one is linear, this is quadratic growth. It's a paraboloid. And the curvature it's decaying linearly in the distance. So R means the distance. Not all curvatures, so here I should specify the curvatures restricted to the level set. To the normal direction to the gradient of f. So this is to restrict it here, and normal direction is faster, so it's quadratic actually. So let me save time and not write that on the board. And again, for what we care about, it's it's linear, and there are some direction where it's even faster than that. Pretty much like in the thick example, right? In some direction was faster than quadratic. Here it's faster than linear in the gradient direction. So that's all the examples I need in dimension 3 and 4. And we're going to start with these examples and try to come up with some classification plans. Okay, so before we start, I need to say a few words about properties. So I'm going to write them on the board, and I'm going to use them freely from now on. And I will not provide proofs for any of them, but I will explain in words a little bit about each, maybe. So they're kind of similar. But there are some distinctive features, so let's start with shrinking. And this is a good opportunity to set up the notation. So for me, Ricci will be Ricci curvature. Riemann will be the Riemann curvature tensor as a tensor, and S will be the scalar curvature. And so there are some properties. One was very early on discovered by Hamilton, that the scalar curvature plus the gradient of the potential is F. There's some normalization that I'm implicitly doing there. So that's an important formula. It connects the potential function to the scalar curvature. Of course, to this I can add scalar plus Laplace. It's dimension half, for the reason that I'm just tracing the Ricci-Soliton equation. So this was Ricci plus Hessian equals G over 2. Trace that, you get this one. These are proved by using Bianchi identities. So you just start with the Ricci-Soliton equation and take derivatives of the Soliton equation. So that's a tensorial equation. Take some derivative, use Ricci-Bianchi identities, and you get this one. I mean, you get that this is a constant. Okay, so this is the formula. Something that's important for later is that, of course, this. This maybe doesn't say much right now, but it will be crucial. It says the derivative of scalar curvature is Ricci in the gradient direction. So it's just a formula. Again, proved by Ricci identities, Bianchi identities, and so on. And then there's a set of equations that we know from Ricci Flow. You can prove them directly here, but they also follow from Ricci Flow. So these are equations for scalar curvature. For Ricci curvature, and for Riemann curvature. This means an expression in the curvature tensor, and for the purpose of these lectures, we are not going to use specifically the formula, just that it's a quadratic expression in curvature. So I guess these are the basic ones that it takes you only a little bit of time to prove. And it's amazing that starting from here you can say a lot. So you can actually get a lot more just from this set. And I'm going to explain a little bit the parts that I'm really interested in. So other facts. One is that the scalar curvature is actually bounded by some constant over distance squared. So r is the distance to a fixed point. So the scalar curvature has a lower bound. And here I'm assuming the Soliton is not flat. If it's flat, of course, this is nonsense. Epsilon positive. So if it's non-flat, and I will assume everywhere that it's not flat, then you have this very useful lower bound. So scalar curvature is actually bounded from below by that quantity. Another important fact is that the function behaves like the distance function at infinity. So the function, the potential is kind of like on the Gaussian, it's a distance square over 4. And the volume of ball of radius r, so this is a name for the volume of the ball of radius r. It's at least linear, at most polynomial. So these are not trivial. So those are, again, with a little bit of work, anybody can find them. It's the Bianchi-Ricci identities and so on. These require a lot more work. The first one was proved by Binlong Chen partially, that scalar is positive, and then by Ben Chao, Feng Lu, and Bo Yang. So I'm combining their results into one statement to save time. This is proved by Huaidong Cao and the Tang Zhu. And this is proved by part of it. The upper bound is proved by the same Cao and Zhu. The lower bound is proved by Jiaping, Wang, and myself. So I'm combining this all these works into 3 statements to save time and also to make it more self-contained. This is very important for later. So it tells you a lot of information about the geometry. I'm not going to prove them, but I need to tell a little bit about the first one because that's important later. I'm going to use that estimate a lot. Of course, second is also crucial. So let me explain the first one. First of all, as I said, the first step is to prove that the scalar curvature is positive. So that's the first step. Then you improve it to even better than positive, to quadratic lower bound. Here this means, I didn't explain, this means the usual Laplacian minus the gradient. So there's a drift Laplacian. So obviously this is a positive quantity. I can definitely say this is less than S, right? So I have Laplacian of S less than S. That's clear. If I can use maximum principle, I will get that the minimum point of S, this is non-negative, so I will get S to be non-negative. Strong maximum principle, I get that either flat or strictly positive. Again, I don't care about the flat case, so I'll just say it's S strictly positive. So strong maximum principle tells you that S is strictly positive. This is again provided you can use the maximum principle. So you can say if the maximum occurs inside, then you have this property. But what if the maximum is achieved at infinity? In that case, you use a cutoff function. And that's very standard. So you use a cutoff function to make the function, to make S have a support in a compact set. When you use cutoff function, there are always problems. You need to control the Laplacian of the distance function. That's what happens when you use a cutoff. The cutoff depends on distance. So you need to control the Laplacian of the distance function. And there is a theory, just like when Ricci is bounded below, and you can control the Laplacian of the distance, you can do it when Ricci plus Hessian is bounded below. You can control the Laplacian of the distance function. So that's how it works. So the quick answer is maximum principle. The more detail is you have to use cutoff. I'll explain more later how we use cutoffs. I will give some examples, and then you get the lower bound. So scalar curvature is actually strictly positive. To get even better, that scalar curvature is epsilon over r squared. It doesn't require much more work. It's actually a very nice trick. Again, maximum principle, but this time to a better quantity. So on one hand, I have that this is less than S. So I'm using the same formula as before. On the other hand, if I compute the Laplacian of 1 over F, and I'm going to skip this computation, but it's a quick one. This one is not equal, but it's almost. So I'm going to be vague here. There are some error terms, but it's almost like 1 over F. And we know from the second identity that F behaves like distance squared. So that's exactly the kind of behavior I'm interested in the scalar lower bound. So now, just redo the maximum principle for a new quantity, which is S minus epsilon over F. So the same idea is here, but now you use the maximum principle for this quantity, where epsilon it's small, so that this is strictly positive inside some domain. So in a ball of some fixed radius. So I'm picking epsilon small enough so that at least inside the manifold this is true. The problem is, how do I get it outside that domain, outside the compact domain? So I get it by maximum principle. On the boundary, I know the estimate is true. At infinity is also true because this goes to 0. And this goes, this is non-negative. So at infinity is true. Inside the domain is true. What allows me to say there is such an epsilon is the fact that scalar is strictly positive. So it may decay very fast, but at least in that fixed domain, scalar is positive. So I can find such epsilon. And then I use maximum principle. I use basically this one as a barrier function for this function, for the scalar. So that's the trick. And you could not do this in one step. So basically it's impossible to do this one in a single step. You have to prove first it's positive, then you improve it to a better lower bound. Right? So that's how. But this is a very standard idea, very standard trick. So there are some other properties that are notable, but I'm just going to stop here with this, and I'm going to start basically the second part, which is about classification. So to save time, I'm not going to talk about steady properties of steady, because that I don't want to confuse people by saying this is true for shrinker but it's not for steady. So let's just leave that for the right time. In the last lecture, I'll talk about steady. So right now, we have good properties for shrinkers. Just to kill off the suspense, I'll just say for steady, things are not that nice. So there's some, the estimates are much worse than this. The properties are much worse than this, but we'll see at the right time. So the second part was about, this concludes the first part about basic properties. I'm sure a lot of you have seen this before, and I try to do it very quickly. Now the second part about classification of shrinkers. So I should say that, first of all, the important problem was in dimension 3. How do we classify shrinking Ricci Solitons in dimension 3? In dimension 3, the only examples are the flat one, the cylinder, and compact. And of course, quotients of those. So let's just say the universal covering must be one of these 3. In dimension 2, it's only the flat and the sphere. So this was the classification. In dimension 2, this is not too hard to see, because you can reduce the problem to an ODE. So it's just an ODE problem, and then you solve it. In dimension 3, this was considerably harder. So Perelman proved it with some conditions, kappa non-collapse, positive curvature, and so on. And then they were removed after some effort. Using those properties, using different arguments, they were removed eventually. So this one required more work. But essentially, it's based on Perelman ideas, and then with different arguments by Ni, Wallach, and Cao, Shen, Zhu. So eventually, this is the statement that they were able to prove. In higher dimension, there is no such classification yet. So at least in 4 dimension, there's no. In higher dimension, there's no hope. In 4 dimension, we're not close yet, but that's the part I want to report, what kind of progress we can make. First of all, I will start with the theorem. Probably that will finish today, which is proved by, the first part, by Jiaping, Wang, and myself. And which says the following. If you have n dimension, so any dimension, but I will need to assume sectional to be positive, then the manifold must be compact. Compact as a manifold, so it must be a compact manifold. It cannot be non-compact. So actually, this statement implies this one in dimension 3. So this is much stronger. Actually, this is what Perelman proved in dimension 3. So in dimension 3, he proved that if sectional is positive and bounded and kappa non-collapsed, we only need sectional positive. Actually, boundedness is not necessary in our argument. But we do it in any dimension. We don't do it with his approach. His approach is very specific to dimension 3. Even in dimension 4, that doesn't work. It's already hopeless. So we do it differently. That's why I insisted a bit on that proof, because it's more along those lines not along the original proof of Perelman. And this in dimension 3 implies classification. According to the Fick example, in dimension 4, it does not imply classification because the Fick soliton does not have sectional positive, not even Ricci positive, right? So that's not good enough. So for the next few minutes, I'll explain how the proof goes. This ends at 50, right? 10:50. So I have 4 more minutes. So the proof of this statement goes like this. So it's a very simple proof based on maximum principle, and it's along these lines. But this time I'm not using it for a function, I'm using it for an eigenvalue, so for a tensor. So I'm going to use maximum principle, but for tensors. So I have that, I saved the formula over there, so I know that Laplacian of Ricci is Ricci minus Riemann Ricci. And I know that the sectional curvature is positive. So it's not hard to see that then you can drop this guy because this will be positive. And therefore, Ricci will also be positive, but also the sectional, this is just sectional curvature. It will be positive. So therefore, I have so lambda of x is the lowest eigenvalue of Ricci. So this implies that because of the sectional positive. So now you see the similarity. I had over there, I had S was the scalar curvature. Here I just have lambda, which is a eigenvalue. So this is not smooth in general, but this holds in the sense of barriers, in a weak sense. Then the same idea is here. This time I cannot prove that by itself. It's not true. We don't know if lambda is positive in general. So I cannot prove that, but it's given because sectional is positive. I know Ricci is positive. So this is given. I don't need to prove it. We don't need the first step. But the second step of this, so just barrier function and so on, shows that lambda is greater than some epsilon over r squared plus 1. So I have a lower bound for Ricci. Itself, this doesn't say much. So you have a lower bound for Ricci doesn't mean that the manifold is compact yet. So this does not imply compactness yet. But we start using other identities. So we start using this one, for example. This one says that the gradient of scalar curvature is equal to Ricci in the gradient direction. So if I take product with gradient f, and I use the lower bound for Ricci curvature, I get that. So the rest of the proof, I don't want to get into details. It's not long. It's just a couple of more paragraphs. So it's a very short proof and very easy to explain. But because I don't have time, I'm not going to explain, I'm just going to give you the heuristics, the idea. So why is this important? It's important because the function behaves like distance squared. So when I say grad f grad s has a lower bound like this means, but it's not really true. You can make sense of it if you're careful enough, but it means more or less, and let me try to be at least correct about this one. It means the derivative of s in the r direction is bounded by some constant over r. When you replace f by distance squared, this is the derivative of scalar with respect to the distance, and so on. Again, f is not really distance squared, so this is not really true, but this is the idea behind it. You integrate this, and you get that scalar must be constant log of r. So it grows very fast. Okay? So this is a step where I can't give too many details, but it's a very short proof. So it's a 2-page proof, and it's any dimension. So S scalar curvature has to grow very fast. You see, from this one, which apparently is useless because there are lots of manifolds that are non-compact and they have Ricci positive in this sense, we can get a lot more by using a Soliton equation. Integrate, I get this. This would already imply Perelman's result in dimension 3 if I assume the curvature is to be bounded. So there is no shame in assuming sectional positive and bounded. And this would already finish the proof because it shows R cannot go to infinity. But we can do better. So basically the last part is to prove that scalar cannot grow so fast. So the last part is to use this equation, integrate it. Where does the Laplacian go? You expect that to be positive because f is distance squared. So when you integrate the Laplacian on a ball, you expect that to be positive, and you can prove it's positive. You get this property. So the average of scalar curvature over larger and larger balls must be bounded in terms of dimension only, so n over 2. And that contradicts this one. Right? So there's no, it's not a big deal, it's not a big proof, it's just maximum principle, and with you combine with the Soliton identities. And this is true in any dimension. In particular, in dimension 4, we need to concentrate, to focus on what happens when sectional is not necessarily positive, or Ricci is not necessarily positive. So what happened in that case? Actually, it's a very interesting question to see if this can be replaced by Ricci in general. And I don't know how to do that for a simple reason. As you can see from this equation, Riemann does appear in the formula. So it's controlling, by saying sectional positive, it's controlling this equation in some sense. If I don't assume that, it's much harder. Okay, so I'm going to stop here and continue next hour.
Any questions from any questions? Okay, if not, you can ask him during the break. So let's think of it again.